Hi, Ken Masterson here. I want to take a look at something which I've recently added. It deals with interactions of one bacteria to the other. With so many bacteria, reacts with what, and all the interreactions become very complicated and usually very poorly documented in the medical literature or the research literature. What I did was do a non-parametric method, the same type of method which I use for the Eureka connecting symptoms to bacteria shifts. And what we have on screen is the simplest case. We have a 3 by 3 square. And what we do is for example, for bifidobacteria, we take a look at every single reading and divide the range into three ranges. The bottom third, the middle third, and the top third. For the other one, we go and we do the same thing. The bottom third, top third, middle third, and top third. And then we go and we count how many are in each one of the squares. This is a technique which often can be referred to as chi-squared. And what we do is we try to determine if the odds of this pattern happening by random chance is there or isn't there. This case, we go on with some mathematics, we calculate it, and as you see, the odds are pretty sparse of it happening by random chance. So we've determined a relationship. With the relationship determined, we can roughly estimate what the degree of strength between the two things. That is, how much one increase or decrease is likely to impact the other. So we have 13%. But wait, stop for a moment. We did 3 by 3. What happens if we do 4 by 4 or 5 by 5 or 6 by 6? Well, behind the scenes, that's actually what we do. We go from 3 by 3, which is the smallest square which we do, and we keep going. And as we go through, we calculate a probability. And we stop with the probability which has the highest probability of not happening by chance, and we show. So here we have a 3 by 3, which is the bottom of the stack. Now we go over to a 4 by 4, and we see with the 4 by 4, the high colors are on line across here and low colors there. This implies that as this bacteria increases, bifidobacterium decreases, and the reverse. In other words, they basically fight with each other a lot. And we see that the approximate explanation between the two is about 17%. So they have a negative effect on each other approximately at 17%. So let's take a look at another one. Here we go up to a 5 by 5. And again, we see the dark colors are diagonal and at the other corners is light. Again, this implies that these are fighting with each other. The percentage here is slightly more than we had before, is 18%. It can go all the way down to 1%. When it goes down to 1%, it means that while we found a relationship, it is a complicated relationship, not necessarily straight lines. So we end up actually excluding those with a very weak relationship in terms of straight line because it just makes the mathematics a lot more complicated. Okay, let's go on to take a bigger example. Here we have a 6 by 6, and if you take a look at it, we're comparing a specific species compared to the genus as a whole. Basically, it's about 36% linearity between the two. And what we find is that the line, basically, as one increases, the other increases, which is to be expected. This is a species of this genus, so we expect them to go up. The fact that it doesn't go up necessarily that smoothly implies that other species of the bifidobacterium are perhaps conflicting, etc. And we notice that the highest percentage is here. In other words, when we have 66% on 66 percentile in one group and 33 on the other group, that's where we get a balance. In other words, Bifidobacterium being the exclusive bacteria rarely happens. Other bacteria in terms of Bifidobacterium also are there. And so there is an interesting combination with the two of them. So it's again something to explore. So where do we use this data? Well, if you go to your sample selection screen, you will see that there are now two items. There is a Y, which uses conventional scientific studies to show the relationships. And we have a Y, citizen science. What we just saw was citizen science. It's not an official publication. It is what we discovered by looking at all the contributed microbiome. So if we click that, we end up going over and seeing for a particular sample, what do we have that happens? In this case, we see a particular species, and we see that one species fights with it, but two others play with it well, which means that those probably contributed greatly for that one being where it is. If we go down, back down to, let's say, Bifidobacterium, there we go. Click that. We now see what contributes to it. High items fight with it. Oops, that's why it's low. High, oops, that's why it's low. Oops, that's why it's low. Oops, fights with it again. It's low. Plays with it, but we don't have many of these. Plays with it, but we don't have many of these. Plays with it, but don't have so many of these. In other words, we see that the bacteria that will help it grow are few in terms of its friendly genuses of the same group, and those which fight with it are high, hence Bifidobacterium is low, which implies that we may want to look at trying to reduce some of the high ones so this particular one has an opportunity to come up. Now, you notice that the lines have slightly different thicknesses. And the thickness of the lines is reflecting what the linearity found in the prior chart was. Remember, we had the linearity from from about 8% up to 36%, etc. So the width of the line indicates how strong the relationship is. That means you can see that this one has actually a weak relationship. These two have stronger. This one actually has the strongest relationship. And what we have over here is we have probably we have three very strong relationships, so they are really pushing it down. Okay, let's go on to another one. Here we are looking at one which is a high. So what we have a whole bunch of bacteria that plays with it, which are high itself, so that reinforces it being high. This is also fine. Lactobacillus fights with it, but guess what? We are low on that one. How about this one? That one plays with it, so everyone just plays with it, and it does some contribution. Doesn't look like it's that thick a line. And the one that fights with it, we are low in it. So the result is you have everybody saying, "Hooray! Keep growing, keep going, keep growing," and nothing to stop. Now remember, the bacteria shown here are the bacteria from your new biome sample. There are other bacteria which are associated, but you may have 0 of those, hence they're not showing on screen. It's only showing what you actually have, and thus it tries to explain why your particular item is high or low, as the case may be. Okay, let's do one more and then we'll call it quits. Okay, here we have a pretty complicated one going on. And if you go through it, you can see that you have things that play with it, which is low, but what we're really interested in is why is it high. So we have several ones which are high, and We have one of the high ones which fights with it, but in general, we have the ones that fight with it are all low, and the ones that play well with it are all high. Okay, this is using the citizen science version. And now what I'm going to do is I'm going to flip over to conventional science one, which is here. Same bacteria, and you got your relationship shown here. You got slightly different bacteria because it depends whether or not a relationship is known. And we have the slowed by, which implies fights with. Again, low amount, it grows high. We have a high amount, should slow down, high amount should slow down. But it's basically the same information, sometimes with different bacteria. Occasionally, you will get one chart showing a bacteria plays well with it, and the other one fights with it. And often it's because the relationship is weak, which means that depending on which study or whatever, it will go one way or the other. In other cases, because the relationship is actually complicated, and if you just look at the right portion of the data, you'll get to one conclusion. Look at a different portion of the data, you'll get a different conclusion. Or how you massage the data. Again, I was using non-parametric methods. Other people tend to always want to use linear regression. You will get different results with the two different methods. Okay, so that's it. That explains, or at least attempts to explain, what I'm doing. In short, I break data into percentiles, and the main reason is frequently the numbers are nicely close together, and suddenly there's a small bunch of numbers which are totally out of sight. If you're working with averages, those really twist the mathematics and statistical analysis. By working with percentiles, I find I have much better result. So the result is I go in, look at one, look through everything else that is connected with it, make a determination of the probability of it happening by chance, and then attempt to estimate how strong the relationship is between the two of them. And for example, in this case, you see very small numbers on the outside, and roughly somewhere down the middle is the where most of the data falls, which means it is sort of these two bacteria plays well with each other. Although it's interesting that if one has none, then the other one has none, which is okay, or very low and very low. Keeps with the idea of playing with each other nicely. So with that, we end up going over and putting those relationships on a network diagram and connect everything up according to which particular bacteria you have. If you go back here, you will or may find that, for example, if you go down all the way to species, that if you go down to one of these, you may find find a beautiful one like this particular species has extremely strong correlation. However, if you go back to the chart, you won't find it listed for a very simple reason. You don't have any of it. So there's the difference between the two. One shows all of the bacteria from all samples, and the other one shows just for your specific examples. Okay, have a good evening. I think I'm ready for bed.